Hello, good morning, afternoon, or evening, depending on where you are. And welcome to this panel discussion section of the GYSS 2022. My name is Lai Choi Heng. I'm from the National University of Singapore, and I will be moderating the flow of this session's discussions. The organizers have set a very challenging and possibly provocative topic for us, unmet challenges in physics. It is fair to say that the diversity in research interests among the participants is great, and all of you must have some research agenda that you have set up for yourself in order to establish your standing as a member of the scientific community. You will have in mind some of the challenges that you would like to tackle, but you might want to hear about the insights from our panel speakers as to what they think might be bigger issues and bigger challenges, and hopefully with the reaction of, why didn't I think of that? Now, even our focus today is on the unmet challenges in physics. Those of you who are not in physics could perhaps also benefit from hearing about the tough nuts in physics and think about what your research focus could help in meeting these challenges. And in these days of international and interdisciplinary cooperation, such an outcome could be very beneficial. We will be calling for questions and comments from the participants, and you will have a chance to raise issues and to give your views on the topics that are going to be discussed in this session. Let me start off with some introduction of the panelists. Professor Takaaki Kajita is the Distinguished University Professor and the Director of the Institute for Cosmic Ray Research at the University of Tokyo. He received his PhD in 1986 and has been carrying out research at the Kamioka Observatory in central Japan using both the Kamiokande and Super Kamiokande detectors. The apical event happened in 1998 at the Neutrino International Conference held in Takayama, central Japan, when Professor Kajita announced the analysis results that provided strong evidence for atmospheric neutrino oscillations. In 2015, he shared the Nobel Prize in Physics for his role in this discovery. Currently, he is the leader of yet another project at the Kamioka Observatory, the KAGRA project on gravitational wave studies. Professor Kajita is also the president of the Science Council of Japan, which makes recommendations to the Japanese government as well as the general society about certain issues. Professor Didier currently holds appointments at the University of Cambridge, and I may not be up to date at this, and the University of Geneva. And he is also the Director Designate of the new Center for the Origin and Prevalence of Life at ETH Zurich. Now, Professor Gill was the first to discover a planet, 51 Pegasi b, orbiting a sun-like star outside of our solar system, shedding light on planetary systems and giving our scientists a new means to better understand the origins of life. In 2019, he was awarded the Nobel Prize in Physics along with two other scientists for his seminal discovery. Now, although 51 Pegasi b is uninhabitable, at least to humans, due to its very high surface temperature of about 1,000 degrees Celsius, its announcement in 1995 sparked a race to find other exoplanets. Well, over 4,000 of them have been found since, and many of them by Professor Gilo himself, with an incredible variety in sizes, forms, and orbits. Ever since the award of the Nobel Prize, Professor Gilo has also been bombarded with questions about life in the universe. Professor Artur Ekert is the Lee Kong Chian Centennial Professor at the National University of Singapore, as well as the founding director of the Center for Quantum Technologies, or CQT, which is Singapore NRF's first research center of excellence. He's also professor of quantum physics at the Mathematical Institute of the University of Oxford. Now, he's one of the co-inventors of quantum cryptography, and his current research extends over most aspects of information processing in quantum mechanical systems. He has worked with and advised several companies and government agencies over the years. He is the recipient of several awards, the 1995 Maxwell Medal and Prize by the Institute of Physics, the 2007 Royal Society Hughes Medal, and the 2019 Mises Quantum Prize. He was elected a Fellow of the Royal Society in 2016. And in his non-academic life, he's an avid scuba diver and pilot. It is interesting to note that these three panelists have something in common. Each of them received the prize in recognition of their achievements that was also awarded to their PhD supervisors. Professor Kajita did his thesis research under Professor Masatoshi Koshiba, the 2002 Nobel laureate in physics. Professor Queloz shared the 2019 Nobel Prize with his PhD supervisor, Professor Michel Mayor. Professor Ekert and his thesis supervisor, Professor David Deutsch, both received the Mises Quantum Prize. Well, there's nothing like a mentor or role model that can excite the passion and sustain the resolve, as well as forging ahead in one's path to scientific discovery. Well, next we will start off the discussion and invite the panelists to share with us, perhaps in a few moments, of their thoughts and on the kinds of challenges, either in their current research area or in a broader context within which their current research initiatives are embedded, or in physics in general, challenges that deserve serious attention and the youthful enthusiasm and passion of our scientists present today. Well, first, I'm intrigued to know that Professor Kajita actually switched his research direction from neutrino physics to gravitational wave studies even before he received his Nobel Prize for his work on neutrinos. In a sense, he probably has multiple perspectives of challenges for scientists in these fields. So, Professor Kajita, can we have your comments and thoughts, please?
Okay, thank you very much. Well, certainly, I changed my research topic from neutrino studies to gravitational waves. Well, that was around 2008. And in fact, before this change, I worked in neutrino physics for more than 20 years. And I thought that was a little bit too long. So I wanted to do something new. And therefore, I decided to do gravitational waves. Anyway, I'm a cosmic ray physicist. And if we look at the universe, there are many very important unmet challenges. For example, we do not know what are dark matter particles. We are sure that there are dark matter particles in the universe, but we do not know what are they. So, for example, this is really a very important issue for us to understand the universe. What shall I do? Shall I continue or ask some other speakers to say a few words?
Well, if you have something more to say about this, or raise some, challenges to our participants, you can do that now, or you can do that later.
Well, okay. Well, then maybe just one more word.
Okay.
I said I worked in neutrino physics, and in fact, in neutrino physics, well, certainly we understand a lot in the last, say, half a century or so. However, we still have a fundamental question about neutrino. We do not know if the neutrinos are Majorana particles or not. This is really an extremely important question, and we have to know within a reasonable time scale.
Okay. All right.
Yeah.
Thank you, Professor Kajita, for the opening remarks. Well, next we perhaps turn to Professor Queloz. Well, when ETH announced last year the establishment of the new Center on the Origin and Prevalence of Life, you actually tweeted, "The timing is perfect." And you welcome the chance to work with scientists in other fields, obviously, right? So what are your thoughts on the worthy challenges on this line of research on either exoplanets and the origins of life?
Well, thank you for the opportunity, I think, to explain a little bit. What I mean, I am into the field of finding planets, and the question of life is looming around and still there, and a lot of people asking questions. And I think it has been quite a difficult topic where little progress has been made, and for the simple reason that, I mean, science is based on data and facts, and we were essentially missing all these facts and all these data. You can have theories, and there are theories about that, but the practicality is difficult. The main reason is life on Earth. I think if you look for the beginning of life on Earth, I mean, there is nothing left. I think all the geophysical traces and mineral traces of life that would be from the first billion years is completely vanished and erased by the nature of the recycling you have on Earth. And now what is happening is actually there is a bit of a change on all of this. So first one, we have plenty of planets right now, and we're finding more and more planets, and we're detecting atmosphere on this planet, and we're studying the diversity of the planetary, structure, planetary atmosphere. And the question is whether there are ongoing life on this planet. We keep coming and keep coming and keep coming, and we want to say something about that. The other reason, I think space has made tremendous progresses, and now we're launching rockets on a daily basis. We're exploring Mars, we will explore Venus, we'll go to the satellite of the giant planet. And we are really in a situation where we can try to probe for life in the solar system, but outside the Earth. And that's a fascinating question. The idea that we are now getting sample for Mars, and tomorrow, maybe in 10 years, we're going to bring this sample back on Earth. We will be studying this sample with great detail and looking for isotope deviation, something that may be telling us some interesting chemistry related to life is happening and has happened, at least in the past, on the first billion years. And then what is going on? It's in the labs. I mean, the chemistry. The chemistry is living a full revolution right now. I think that the technology used in the chemistry, the equipment they're using to analyze, very, very complex. I mean, it's fascinating. You can give something to a chemist, and they're going to give you the detail what it is right now. It was not possible 20 years ago. And that has been so much progress on that front, in addition to the progress being made on what we call computation chemistry. So we can compute chemistry into computers. So you can do chemistry not in real, but you can do computers chemistry. And the computer becoming more and more powerful. There's more and more potential here. And tomorrow you can really explore millions of combinations of chemistry in a couple of minutes. And I would have taken, years of chemist work to be done. So all this together is unique. And I think we are now in a situation where we can seriously start making progress on the questions of, first, the origin of life on Earth, the way we understand it, and the question is possible life elsewhere, and the connection with life on the planet. And this is happening now, and it's the reason why we are establishing these centers. I'm not the only one. I mean, it's happening in Harvard, it's happening in Chicago, it's this discussion in Caltech about doing the same. So there is a similar center being built up in Munich. So there's a couple of centers, and this center have a very simple goal. We have to break apart the old-fashioned structure of science. We cannot keep working with the physicist in one corner, the chemist in another one, the geophysicist in another one, and the mathematician here. We have to bring them together, and we have to bring bridges between these disciplines. And that's the big challenge, essentially, to me, of the physics of the future, is being able to be more flexible and trying to benefit from what is being learned by this other kind of way of working. And I have an anecdote to give you an idea how far we are. I made a paper recently with one of my colleagues doing biochemistry. So I brought some equipment, from astrophysical equipment, into a wet lab. And we did the paper. It was a great lot of fun. And the most fun part was the paper when we start discussing what to write in the paper. And I remember the point when I said, oh, but we need to put some error bar on your numbers. And you look at me, I say, we don't do that in chemistry. So to give you an idea, I think how much the culture is different and how much is fascinating and exciting to work into that. So that's what I'm doing right now.
Right. Thank you. I think in addition to the technical challenges, obviously the management and organization of research teams these days itself poses a strong challenge to the culture. Thank you very much. Before we get into any kind of questions, perhaps we can invite Professor Artur Ekert. Artur, over the years, you have steered CQT onto the world map of quantum information science. And the works done at CQT are gathering international respect and recognition. What are your thoughts on the remaining and perhaps even emerging challenges that need to be addressed in the years to come?
Well, thank you, Choi Hank, and thank you for having me for this discussion. In a way, my answer is a follow-up to what my predecessor actually said. So I think working in quantum information science or working in the field where you're trying to look at information from the physicist's perspective, right? So you realize that information is physical and what you can do about information depends on the underlying laws of physics rather than mathematical statement. So it's kind of amazing that historically we have a theory of information that is, many people think, purely mathematical, which it isn't. So the big challenge in this field was exactly the same. So you had a mathematician in one corner, you have a computer scientist in another, and you have a physicist, and you start learning from each other, right? So you try to explain to a computer scientist certain ideas about physics, about quantum physics, for example, and then you learn about computational complexity from computer scientists who have their own way to define complexity of processing of information. Then you talk to a logician about the nature of mathematical truth, and you put physics into this. So it's kind of interesting to see that, you know, we created a certain silos, right? So historically, universities have Department of Physics, Department of Mathematics, here's biology, but nature doesn't know about those divisions. So there's lots of interesting stuff to learn in between them, and I think that's a big challenge. The challenge is also to educate people to be able to do it, because each discipline develops sort of its own language, right? And people use this language. And somehow you have to also come up with a set of tools that allow you to work across different disciplines. So I think for me, I think that's quite a challenge to both to, you know, carry on and do research in this field, but also develop a set of tools and methods that would that then you can just pass to students and to the next generation that can explore it. So I think, to me, the big challenge is to understand the nature of information, looking at it from the point of view of not only mathematical, but what it really is, how you can process it, looking at it from you know, assuming that it is physical, looking at it from more like a physicist's point of view. Even though, you know, even now I'm sort of like a slave to this language, right? Because I'm saying physicist, a mathematician, a computer scientist, which is already not quite right. So at some point we have to develop more universal language.
Okay, thank you. Well, I think what we will now have some time to address some of the questions that have already been sent to us. Right? Obviously, the number of questions is likely to be large, and the time allocated to this particular session is limited. So I'm going to have to exercise my moderator prowess and prioritize them, and ask for your forgiveness if we are unable to get to your questions. Before the session, we had actually sent out a sort of a request for people to send in some of the questions. So we will start with some of these. Right? The first question, in fact, is, well, probably directed to Artur Ekert from Neelkant Kundu from the Hong Kong University of Science and Technology. And the question is, when will quantum computing and communication become a mainstream technology for everyday use in our mobile phones and our laptops? Right. Obviously, when can I get one from Amazon.com?
Yeah, well, there's a very simple answer to this question on my side. I don't know, and I don't think anyone knows about it. One thing that I should say, there's lots of hype at the moment about quantum computation. It's you keep reading about it, and some statements that you can hear are truly outrageous. It just, from the scientific point of view, the first thing you have to do is to really be more precise. What does it mean really to have a quantum computer? At which point a quantum device that you can control and do something about it becomes a computer? So now we are talking about few quantum logic gates that you can put together. We are talking about having very noisy quantum systems that you can control. And the challenge is, to what extent those noisy systems can do something interesting and useful for us. A fully fledged quantum computer that will have enormous computational power is probably, years away from us. I don't think we'll have one in 10, 20, even 30 years. But we can have useful devices in a not too distant future. So I would say, I don't think you can just get a quantum computer or install a quantum app on your quantum iPhone. That will not happen in the next 20 years or so.
Okay. Well, okay. I will save up for that. Okay. Let us try to move on to the next question from Debobrata Rajat. This is a question actually on gravitational waves and is originally directed to Professor Queloz, but perhaps Professor Kajita, you can also chip in and comment. And the question is, how difficult is it to measure a gravitational wave background present, and what are the implications if it is experimentally observed? Before we get into comments from the panelists, perhaps I can advertise that we're going to have the next question from, let me see, Disha Kapasia, and directed at Professor Kajita. So yes, how difficult is it to measure gravitational waves background, as well as, if it is measured, what implications does it make? Professor Queloz or Kajita? Professor
Well,
Kajita?
I think Professor Kajita should go ahead. I mean, he is working in this field since so long, so he has the whole expertise to answer better than me.
Okay.
Okay, thank you. Well, certainly, the gravitational wave background is extremely important. This is an extremely important item for us in the measurement of the universe. And if we observe this gravitational wave background, we understand that at the beginning of the universe, there was a special period called inflation. At that time, the universe expanded tremendously. So this measurement will be really important. And another question is how difficult it is to measure this background. Well, typically, people would like to observe gravitational wave background by precisely measuring the polarization of the cosmic microwave background. And it seems to be extremely difficult, but people think that this is not impossible. So we hope maybe within the next 20 years, we get some measurement of the gravitational wave background. Okay?
All right. Thank you, Professor Kajita. Professor Queloz, do you have anything to add? I think he's muted at the moment, right?
Sorry for that. I think Professor Kajita is absolutely right. I think this is an amazing measurement, and the day is going to happen. We may have some surprises. I'm pretty sure, because there's something we have to admit. I think the cosmological model works very nicely, but we still have a couple of issues here and there, and we cannot reconcile with the macroscopic size of the universe. So we don't match the two together. So we should be open for surprise here.
All right. Thank you. All right. Do we have Disha on the line? Okay, Disha, would you like to introduce yourself as well as ask the questions, please?
Hi. Thank you so much for this exciting discussion. My question is to Professor Kajita. Both the projects you were associated with, previously the neutrino detection for neutrino oscillations and now currently gravitational waves, they are projects which are long-term in planning and to decades before their detection. So what was your motivation and challenges to continue in these two projects?
Well, thank you very much for this question. Well, certainly my motivation is to understand the universe, to understand nature, that's all. And we know that it takes time. But even if it takes time, we'd like to know the secret of the universe. That's the whole motivation.
And what are some of the main challenges that you found in your career?
My main challenge, or?
Yeah, like a part of the collaboration, because these projects are from a large collaboration. So of course there are like challenges that you need to discuss with everyone. So what were the challenges you faced?
Yeah, thank you very much. In fact, now I'm working in a gravitational wave project. This is called KAGRA, and this is an international collaboration, mainly from the Asian countries. And we have about 400 people. And of course, as a collaboration, we have to discuss. However, now the challenge is, during the last 2 years, we are unable to meet physically. I found, well, certainly nowadays we have technologies to discuss online. However, I realized that it is really important to have the face-to-face discussion physically. So at present, this is the biggest challenge for me.
Thank you so much, Professor. And thank you everyone for your insights.
Well, do the other panelists share the same sentiment about, face-to-face versus email and virtual meetings as one of the challenges in actually tackling some of the physics challenges?
Well, that's obvious. I think what we have learned in doing this pandemic situations is we should maybe pay more attention to the few face-to-face meeting. I think we also learned that we don't need maybe to do only face-to-face meeting. We can do quite a lot of the work remotely, but there is a balance that we need to strike here. And when we have face-to-face meeting, we should maybe value the quality of the meeting as well, with all the social element as well. And that was pretty obvious. I would say for the student, that's a very difficult time. And I see my students, they really have difficulty to cope with the situation because they need this. You were mentioning this mentoring element between the senior and the learning part of it. And this is really essential to the science. We need this real life contact and these interactions, informal interactions between the people. And I think these are the ones that are suffering the most of this situation. Hopefully we have learned for that, and we are seeing the end of it, and hopefully we just manage not this to happen again, ever.
Yeah, I exactly had the same sentiment on my side. I think there are many meetings that for which human interaction is really important, especially the brainstorming things where you just want to come up with new ideas, where there's not like a schema, a specified agenda to the meeting. Then it's much easier to do it face to face. But we also learned that there are many meetings that are absolutely, quite okay to deal with remotely.
Okay, that's selectively useful and not so useful meetings, virtual meetings. Thank you very much for your comments. There are a couple of questions that have shared a certain commonality, namely interdisciplinary science and particularly the approaches that are existing in each of your individual disciplines. So I will not call upon any one of these people who are asking the question, but let us sort of like have a chance to have the panelists comment on this before we call on, let me see, Panyawut Tonanon on directed, the question is to be directed to Professor Queloz about the kind of devices that you're going to be sending into space. All right, so interdisciplinary collaboration and interdisciplinary communication, right? Do you see that as an obstacle in your research fields? Maybe we'll start with Artur.
Maybe I can.
Oh,
yeah.
I see. Okay. Yeah, go ahead, please.
No, please, Artur, if you want to start. That's fine.
No, that's fine. Just please go ahead.
Well, yeah. Well, I think there is no limitation to what we're doing. It's just the limitation that we're setting to ourselves. So we should really be open-minded and trying to find out the best way to do what we have in mind. And that's my first comment. No, of course, we are living into a society with structures, with funding agencies, with a lot of regulations. So we have to play the game as well. And I think we have some responsibility when we're becoming at a stage when we have an impact on the science because we have more seniority. We can really, direct a bit better what we're doing. To explain, and I'm spending a lot of time to explain to funding agencies, admin and director here, because some of them they don't understand. There is this micromanagement spirit that they keep having when they want to enforce framework, they want to enforce controlling, they want to enforce all this management skill that may be perfectly fine when you operate maybe a company that is moving people around or but it's not applicable to science. So I keep telling, let the science do the job and let them work peacefully and the way they like, which means breaking a lot of structure, which is very old-fashioned. And my main battle right now is on the peer review mechanism, which is, I think, not functioning the way it should be. I think if you keep asking the same people to peer review the same other people, you end the same result at the end. And you have very limited vision, and you never build up long vision. And it's difficult to expand beyond your usual field of competencies. And the fact you limit the boundaries most often of the applications, limit itself the growth and the possibility of the funding. And that's quite amazing to realize that most of this multidisciplinary exercise I'm doing are funded on private way. And this is foundations, and they operate in a different model. But when you go for state funding system, it's very difficult. And I'm battling on that aspect. But I think the peer review mechanism and the structure of the funding, I think if we can fix that, everything will follow, because I do believe the scientists are doing what they're doing because they're extremely curious, and nothing will stop a scientist to learn what they need to learn, even if it's not something they have learned in the past. And I think there have been people moving field. I think Professor Takaaki is a very good example that he started somewhere and he goes somewhere else. And I kept learning every time. So that's okay. The problem is the structure of the academic, I think the way the curriculum is being built on, and also the way the funding agency of functioning. And this is where we have to work, and we have to work hard and loud.
Okay, Professor Ekert or Professor Kajita, do you have anything to add?
Well, actually, the same. It's. I would just repeat the whole narrative.
Yeah. Definitely, I think that is a sort of a trend that is becoming stronger and stronger. We probably can do a whole lot more if we were to have interdisciplinary teams that work together, I think, on a mega project like this. Okay, so I think there's a question by Panyawut Tonanon. Is he on? Yes. Can you introduce yourself and ask your question, please?
Hi, thank you very much. My name is Panyawut. I'm a Thai graduate student in NTU, Singapore. Luckily, I'm here. So my question, Professor Queloz, is that since we are sending the James Webb Telescope, and it's an instrument that is slightly different, because if I remember correctly, Hubble telescope focusing on visible light, and James Webb Space Telescope is focusing on IR, like IR region. So my question is that, can you give us a glimpse of what device we are sending next after this? And what information are we expecting to be getting from them, and how it can bring us closer to understanding how exoplanets and life in the universe works? Thank you very much.
Well, thank you. Well, when you want to study the universe, you want to have as much option that you can. So I think the big development right now is to grow the size of the collection area or the resolution, and also to expand all the wavelength, including some wavelength which is not wavelength in a sense because they're not electromagnetic but gravitational waves, which is also a way you can use to probe the universe. So we're doing it in these directions. That's why we're building gravitational wave observatories and facilities. That's why we're building gigantic telescopes on the ground. And that's why we're planning to build the next generations of the next series of space telescopes. Now, infrared, there is a good reason why we go in the infrared. Well, if you want to look back in time in the universe, everything is moved to the red, and something that would be visible in the blue and even the UV and would be seen in infrared. So if you want to see very far in the universe, you have to look in infrared because of the red shift. That's a very simple reason. Now, a lot of exciting science is what we call the cold object in the universe. So you have a lot of cold objects, and one of them is the planets, for example. They're cold compared to stars and to other objects. So this is really why you want to go in the infrared. I mean, the Earth, the peak emission of the Earth is 20 microns. So if you want to go in this direction, that's why you want to infrared. So there will be more and more infrared. And that's a new technology. It's only a technology that has shown up in the 60s. And first, it was only military base. I know it's pretty easy to get an infrared detector these days. And this is why infrared it's a fascinating wavelength. That's the reason why we want to push in this direction. But maybe we can hear something about the gravitational waves, because there will be, I think, gravitational waves telescopes. In a way, they are already, but that's a complete new way to see the universe. And I'm fascinated by this topic. This is so amazing.
Okay, Professor Kajita, would you have something to add?
Yes, thank you. Well, certainly, if we have new tools to measure the universe, we understand the universe better. And certainly, gravitational wave is really a completely new tool to understand the universe. And therefore, we expect a lot of exciting science ahead of us. And, well, about the infrared, well, certainly infrared is for optical, but let me speak with an analogy. At present, the gravitational wave detectors on the ground are sensitive around the frequency of about, say, a few hundred hertz. Now, of course, if we want to look back the universe, we want to be sensitive to the lower frequency. However, we have a problem on the Earth. We cannot avoid the motion of the ground, which are typically bigger in the lower frequency. Therefore, people are thinking to launch a gravitational wave interferometer into the space. This way, maybe, say, in 10, 15 years, we could measure lower frequency gravitational waves. So we have, again, really exciting future.
Thank you. Thank you.
Thank you so much.
Okay. There are also a couple of questions which are directed at all three panelists members. It's about, my comment about you sharing the same prize with your PhD supervisors. All right, so we will do that, but later, next, after that, we will go to a question about the role of data in addressing the scientific challenges that these days. The question is from Sri Kulna Nilnori, which says, understanding science is based on data nowadays. Actually, understanding science has always been dependent on the data. But in any way, let's try to address the question next. Right now, I think the question, common question from several participants is that, to what extent did you do you settle on your research interest because your supervisor says so, or did you sort of step onto something that on your own? Who would like to go first?
Okay.
Yes, Professor Kajita.
Well, thank you for this question. Well, it is true that I joined the Kamiokande experiment. Well, this experiment was initiated by Professor Koshiba, and well, certainly I was excited to hear the scientific goal of this experiment. Therefore, I joined. But during my studies using the Kamiokande data, I realized that the neutrinos are quite interesting. Therefore, at some point, after getting my PhD, I changed my research topic within the same experiment from the proton decay analysis, that was my previous analysis, to neutrino studies. So, in this sense, my research depends partly on my thesis advisor, but partly this is my own.
Okay, thank you. Yes, Professor Professor Gill?
Yeah, happy to share my experience on that. Well, on the reason why they are quite often good student and good supervisor, I think my view is very simple. I think the good student are attracted by a good supervisor, by a good professor. So, and then the professor likes to be working with the good students. So of course, there is a selection effect and on that. And there is a lot of series when you see very good professors attracting students, becoming themselves, amazing professors, and they have good students. And there is what's called families like that you can trace back, which is not a surprise. This is how the system works. It's like a sport game. I mean, the best team attract the best players, and that's what it is. Now, in the term of whether what we're doing, is what being been told. Well, I would say just the opposite, because what makes the system working, in a very efficient way is it's the energy and the creativity and the spirit of the youth, which is meeting the experience at the same time. And that's a terrific, I think, mixing. In my case, I was not supposed at all to find a planet, but we did everything we could to enable a planet to be found, but of course nobody would have guessed there would be one. Well, it was a surprise, actually, and it was not part of my PhD, but when you work together the best you can and the best way, well, you find out many things that is a surprise. So it's not exactly that being told, it's being in the right surroundings, having all what you need to develop yourself and to unleash your creativity, because it's about creativity. And that's pretty clear, and I see that every day. I mean, I love working with my PhDs, with my students, because they're bringing so much creativity and energy and ideas that I can have. And that's the way science works. We have to remember ourselves. I mean, the science we're doing is possible because of the science of our peers in the past, and we can trace back down to Galilei. If you're talking about the data, we're all a child and grandchild of this long series of scientists. So science really is kind of a family stories. So we have to give our knowledge to the young generations, and the young generation is giving me and giving us the energy and this creativity that they have, and they challenge what we're doing, which is good. So I tend to joke about that. I say when a PhD supervisor tell you what to do, just do the opposite. I mean, you have more chance to get more creative if you believe this is what you have to do.
Thank you. That's good advice.
Well, I'll be careful with the advice.
Artur, would you have something to?
Yeah, well, I can only agree with that. I have to say that indeed, it's just like if you, well, at least in my particular case, I ended up in just being curious and walking around talking to people, trying to find the answer, and then I ended up talking to David Deutsch. I don't actually know whether he really wanted me as a student at all, whether he wanted any student at all. But I was persistent, and perseverance paid off. And then we started talking about interesting stuff. And then after that, we started writing papers and discussing things. But it's not just one person, Choi Hank. It's just when you go through life, your scientific career, many people affect your thinking in a different way. Like on my path, I found you, for example, on my path when I came to Singapore. You were certainly a sort of inspiration for me how to in the Asian environment, to understand a little bit more Asian culture and how to work more effectively with my colleagues in Asia. Without that, it would be much more difficult to do anything at CQT. So you have supervisors. Some of them choose you choose some of them. Sometimes it works, both ways. Sometimes it works one way. But actually, at the end of the day, it's about you and your choices, and try to realize that you are probably the average of 5 most interesting people you are surrounded with or you interact with. They shape you, and so choose them wisely.
All right. Well, thank you very much for your comments and advice. I think the supervisor-graduate student relationship is, I think, getting more and more two-way traffic than before, I think. I recall some of the stories about Enrico Fermi. Whenever a graduate student came up to him and say, I would like you to be my supervisor, he would take out a notebook from his drawer and say, this is a list of questions that I cannot solve. Pick one of them and do it. Then you can teach me something. So yes, I think on the one hand, a good supervisor could in principle provide you with the inspiration and maybe a little bit of guidance and advice coming from their experience. On the other hand, as some of our panel speakers raised, your imagination, your independence, your interaction with your other faculty members or graduate students could also have very immense impact on what you're going to develop. Okay, I think we did not, do we have an answer? Yes, question right in the line. Yes, please, go ahead.
Hello.
I'm sorry, before we go start this question, let me try to advertise the next one. I think we are going to be looking at a question that is something to do with data in modern science. Oh, I'm sorry, that has already been done. Sorry. So the question is coming from Zhang Zuocheng, who has something to do with computation. I think, okay. Yes, please, go ahead, ask your question.
Yep. First of all, I would like to thank you for giving me this such a good opportunity to ask you all that we know that to understand the science is based on the data that we collect, right? And how do we know which kind of the data that can explain the unmet problems or unmet challenge that we are going to solving?
Anyone from the panelists would like to volunteer some comments?
Yeah, maybe I can try something here, because there is something that I think which is hidden behind the question, which is very important, which is the way that science communicate what they're doing. So it's good to remember clearly that the science is driven and based on the data collections, whatever data you have in mind, and the difficulty that we are experiencing these days with the communications to the public at large and to the decision maker. I can think about, this global warming situation, so maybe in the COVID, explaining what they have to do, what needs to be done, is the intrinsic complexity of the data sometimes. It's not anymore the science of the 16th century when you could essentially see, you cannot do like Galileo doing the experiment and see things rolling into a ramp and this. It's not working like that. I think now we have clearly extremely complex equipment that is being used, and this disconnect the direct feeling, the direct perceptions, and this called common sense. It's just irrelevant in this case. What is a common sense? When you look, I take this amazing equipment of my colleagues doing gravitational waves measurements. When you look at this, what is a common sense telling you? Nothing. This is just a piece of material somewhere, and it does nothing move. And what do you do? There's a lot of electronic stuff, and there's nothing you can learn about. So I think this is a real difficulty for science at large, and I think we should be more aware of that. And we may want to spend a bit more time in the communication aspect, because for most of the people, they just don't understand what we're doing, and they don't understand that most of what we're doing are rock solid based on data, even if these data are awkward, even if some of the data are coming from a telescope which is behind the moon. There is a real data, there's a real telescope, there's a real observation. But only thing you see is something like an electromagnetic signal you get on your computer. So the data connections, and that's what you said. How could you use the data to find things which is unknown? Actually, there is no problem with that, as far as you understand what means the data. And I think the problems right now is understanding what are these data. And global warming is the best example. I think global warming is known from the science since the 80s. It was clear-cut understood. There were no debate about what is the situations there. And then you have seen people arguing for 30 years on nothing, essentially, because they did not understand the data. And you had this absolutely amazing remark from well-known, politicians saying, "Oh, look, today it's very warm. So, sorry, today it's very cold. So, what do you think about global warming? It's snowing today, so there is no global warming." So, I think this common sense, which is the way we have, does not apply into science, and we should kill the common sense. It doesn't work in science. It's rational thinking, and that's the big challenges. And I have no solution for that. I'm just aware that this is one of the biggest possible challenge, is communicating science, and becoming even more complicated because the equipment we're using is even more complicated, and will keep growing in complication. So that's my take on that point. There may be other views.
Thank you. Any other comments from the other panelists? This is, I think.
Okay. Well,
yes, please.
Yeah, let me answer to your question in a completely different way. Well, certainly data are extremely important for science, for the advancement of science. There's no doubt. And in fact, in order to get a meaningful set of data, you may have to design the experiment or observation. For example, in gravitational waves, you have to, before constructing your experiment, you have to estimate or calculate your noises, and also you have to calculate your expected signal. So before getting the scientific data, you have to really carefully design the experimental setup. And this is really a very important part of our scientific activity. Okay, that's all from me.
Thank you very much. Do we have time to?
Thank you.
Well, I think I've just been told that our time is pretty much up. So I think let's all thank the panel speakers for their time and thoughts. And thank you very much for your participation. Appreciate that. Thank you.